So TGIF, everybody. Just wanted to take a quick look at the schedule with all of you. And it's Friday. And so today we're going to begin Chapter 2. Hopefully you saw that I posted an announcement on Canvas that I made a video that covered the remainder of Chapter 1, the part about significant figures. So that's all been covered. And so I won't be going that over in live lecture. Again, I recorded a video on that, and you can watch that. It is available for your perusal. And so today is August 28th. We're going to start looking at Chapter 2, talking about the atoms, molecules, the periodic table, how to name molecules. So we'll get into that a little bit, and how to name ionic compounds as well. And I just want to remind you that we have 2 Learn Smarts that are due on August 30th, and I went into Connect this morning. I'm actually looking at it right now. I see that 86 students have submitted it, and that is fantastic. 43 people haven't even started it, and 17 people are in progress. So for the 43 people that haven't started it, please start your Learn Smart as soon as possible. Now, when you log into the Learn Smart, or when you open the Learn Smart, what the Learn Smart is, it's a guided reading assignment. So you'll actually see the chapter, and you will see that most of it is grayed out. Okay, most of it will actually be grayed out, but there is some text that you can see that is clearly visible, or more clearly, I should say, and that's basically the highlighted text. And the whole idea behind the Learn Smart is for you to read the highlights of the book, and then you'll see a button or a link in the lower left corner of your screen, and it will say practice. And you have to complete the 20 questions that are in there in order to complete the assignment. So you don't just read it and get the points. You have to complete the questions that are in there. And again, most people have already done that. But if you haven't, I just want to remind you that you've got to complete those questions in order to get credit for that Learn Smart. Also, if you look at your grades, so you'll see there's under the grades, I'm opening up right now, you'll see that there is a space for a grade for the Chapter 1, what does it say? Chapter 1, Keys to Studying Chemistry, Definition, Units, and Problem Solving, and you have a place there for points. Okay, and if you completed the Learn Smart and got 5 points, it's the maximum you can get, and I see that everybody that's completed it has 5 points, literally everybody, if I scroll through. Okay, so make sure you complete that assignment. If you don't complete that assignment by the 30th, I'm going to go into Canvas and I will put a 0 by your name, so you will lose those points. And I've noticed that many people have already completed Learn Smart 2, and a bunch of people have completed Learn Smart 3. So remember, Learn Smart 2 is also due on the 30th, as is Learn Smart 3 is due on August 31st. So there you have it, folks. Okay, so make sure you get the Learn Smart done. Okay, all right. So somebody says, how are the Learn Smarts graded? And like somebody said, you just have to complete it to get all the points. So it's pretty much free points. And that is why if you don't complete it by August 30th, at least Learn Smart 1 and 2, I will put a 0 next to your name. I don't want to do that. That doesn't give me any pleasure whatsoever, but I will have to do that. So make sure you get that done. All right. Well, that's enough about that. And let's get started on Chapter 2. This is really where the rubber meets the road. Somebody says, are the Learn Smarts the homework or the Connect? Okay, if you go into Canvas and you click, if you open up our classes Canvas page, all you have to do is click the assignments link on the left-hand side and scroll down. You'll see something that says Learn Smart Assignments. Those are the Learn Smart assignments. You'll scroll down and you'll see homework assignments. Those are the homework assignments. All right. Well, let's keep moving here, and let's take a look at Chapter 2, so the components of matter. We're going to start right away talking about elements. So we're going to do some definitions for the components of matter and an element. We spend a lot of time talking about elements in chemistry. You can imagine the element is the simplest type of substance with unique physical and chemical properties. An element consists of only one type of atom. So that's really important that you understand that an element is only one type of atom. It cannot be broken down into any simpler substances by physical or chemical means. And I know that some of you are thinking, well, What about elements like uranium? Isn't that radioactive? Can't uranium-238 decompose into uranium-235? That can happen, of course, but that's nuclear chemistry, and that's not what we're talking about right now. And some examples of elements, well, we could sit here and list, over 100 of them, but elements that are going to come up a lot in chemistry are things like hydrogen and carbon and nitrogen and oxygen and fluorine. What else? Neon. And then some of them have atomic symbols that seem like they don't even have anything to do with the name. Things like tin, the atomic symbol for tin is SN. What else? Something like lead, which is PB, there we go, lead. Something like gold. And there are historical reasons why those elements have those atomic symbols. Well, now that we've defined what an element is, let's define what a molecule is. And it says here that a molecule is a structure that consists of two or more atoms that are chemically bound together and thus behaves as an independent unit. So when you have two or more atoms binding together, okay, with chemical bonds, and they behave as an independent unit, that is the definition of a molecule. And I'm sure you're all aware of different molecules, but I can give you some good examples. For example, water, that's a molecule. If I have carbon and 4 hydrogens together like this, that's called methane. It's one of the major components of natural gas. If you read the news, you've probably heard of greenhouse gases. Carbon dioxide is a greenhouse gas. If you write a nitrogen with 3 hydrogens, that's the formula for ammonia. And if you're studying biology right now, I bet you've seen this one somewhere along the way. If you've studied, the glycolysis or the Krebs cycle, you've probably heard of glucose, which is C6H12O6. Anyhow, we could spend a lot of time on that, but let's take a look at these pictures here. On the right, it says the atoms of an element. So you notice that we have one type of sphere. And then the next one, it says molecules of an element. And sometimes students think, well, that's contradictory. No, it's not, because some elements do exist as molecules, and we will talk about that in a little bit. Anyhow, let's keep going and talk about some more definitions for the components of matter. You're going to hear me say the word compound all the time in chemistry class. We're always talking about compounds, and a compound is a substance composed of 2 or more elements that are chemically combined. And we can have 2 kinds of compounds, and we're interested in ionic compounds and molecular compounds. And so if you have an ionic compound like sodium chloride, and if you're like, how do I know that's an ionic compound? I'll get to that. I will definitely get to that. But I just want to put this bug in your ear before we get any farther, that sometimes students will say a molecule of sodium chloride. Well, sodium chloride is not a molecule. It's an ionic compound. And again, I'll give you more detail about that later. But you can see here that we have molecules of a compound. You can see that there's 2 or more atoms combined there together, and they are behaving as independent units. They even have some motion lines. Wow, that's quite the picture. Anyhow, a mixture, it's, I'd say relatively intuitive. A mixture is a group of 2 or more elements and or compounds that are physically intermingled, and a mixture can be physically separated. Before we move on, I want to give you, I actually wanted to move on to the next slide right here, and talk about some properties of sodium, so the element sodium, the element chlorine, and sodium chloride. Okay, so let's take a look at what the heck is going on in this slide right here. Okay, so if you've never seen sodium before, I'm going to move this guy, I'm going to move it up to the top here. Okay, so if you've never seen sodium before, sodium is a metal. Like what? Sodium chloride? Yeah, sodium is a metal. Okay, so sodium is a metal. It's a soft metal, and this is sodium shown right here in this picture. So sodium over here, and sodium is such a soft metal that it can be cut with a knife. So you can actually cut it with even a butter knife. You can just take it and cut it. And the reason, and if you're like, why is that person cutting sodium? Well, the reason why we cut sodium generally is because if you want to do a reaction with pure sodium, sodium oxidizes very quickly in the air. And so you have to cut off the sides of it so that you can expose a fresh surface. In fact, sodium is so reactive that it has to be stored in what's called mineral oil. So there you go. You can see that sodium is clearly a metal. What else? Sodium has a melting point of around 97.8 degrees Celsius. Okay, it's got a boiling point that's pretty darn high. Anyhow, you can see its color. It's silvery. It's got a density of pretty close to 1. It says behavior in water. Well, I'm sure somebody in the class has Googled a video of somebody throwing sodium in water. I wouldn't recommend it. In fact, I saw a guy when I was in graduate school light a cigarette with an ice cube. And the way he did that was he put a piece of sodium in the end of it. Please don't try that at home. Anyhow, you can see next we have chlorine. So chlorine is very different from sodium. Chlorine is not a metal. Chlorine is actually a gas. Okay, so this flask right here, this is some chlorine gas that's in here. Okay, so some chlorine gas. It's got a much lower melting point, and that's because it's a gas at room temperature. And you can see that it's a yellow-green gas. It's got a much lower density, and it actually does dissolve in water to some extent. Now, you can react sodium and chlorine together to produce this compound, this ionic compound called sodium chloride. And the take-home message of this slide is look at the properties of sodium chloride. They are very different from the elements from which it is made. You can see that sodium chloride has a much higher melting point, 801 degrees Celsius, than either sodium or chlorine. What else? You can see it looks very different, right? It's a white solid, right? This is sodium chloride. That's the formula for sodium chloride. You can see it's got a very different density, okay? And it dissolves freely in water. Okay, so we've made an ionic compound, and its properties are very different than those of the elements from which it is made. Let's really get the wheels turning here and take a look at a sample problem, okay? And this is not meant to be some kind of, destroyer or anything. This is just some kind of problem to get us kind of thinking about what we're talking about right now. It says the following scenes represent an atomic scale view of 3 samples of matter. Describe each sample as an element, a compound, or a mixture. I'm going to throw this out to my students who are listening right now. Could anybody help me with A? Does that look like an element, compound, or a mixture to you, based off of the pictures that we looked at earlier?
Compound.
Yeah, absolutely. It's a mixture. Yeah, I see that in the chat everybody's writing mixture, or most people are writing mixture. Yes, it's definitely a mixture, okay? Because you can see we have some kind of compound here, we have a totally different compound here, and we have another compound here. In fact, this is a mixture of 3 different compounds. So you could say a mixture of 3 different compounds, but what do you see here? This is a mixture. If we take a look at B, okay, what about B? Could anybody help me out with that one? Yeah, absolutely. This is just an element, right? You see we only have one type of sphere, and so this is an element. And then C is a compound, right? Because C is the combination of 2 different elements here to make this compound, and you can see how they're behaving all freely, but they're all identical. So it's definitely not a mixture. And so this one is a compound. So there you go. We've been able to identify a mixture, an element, and a compound from these nifty pictures here. Now let's kind of switch gears, and there's a lot of gear switching that's going to be occurring today as we're still kind of in the beginning or the starting phases of the class. And I want to talk about something that's called the law of mass conservation. I'm sure that some of you have heard this before. And the book goes into a bit of a dog and pony show where he spends all kinds of time explaining where the law of mass conservation comes from. But anyhow, that's more of a chapter 1 thing. But the law of mass conservation is simply stated that the total mass, so right here, the total mass of substances does not change during a chemical reaction. And you can see that there's a chemical reaction going on right here on this slide. They have a balance. There's a balance here. And what they're doing is they're taking an Erlenmeyer flask that has a solution of lead nitrate. So this is lead nitrate right here. And then they have a graduated cylinder with some sodium chromate in it. And you're like, well, what's lead nitrate and what's sodium chromate? We're going to get to that, okay? But you can see that those 2 solutions have a certain mass, right? They have them balanced out with these weights right here, okay? Everything is equal. You can see that the balance is right in the middle here. And what they do is they take all of the sodium chromate solution and they pour it into the lead nitrate solution, and they actually end up forming 2 new compounds. They form sodium nitrate, which is soluble, in water, and that's what the lead nitrate solution is in. And they also form another compound called lead chromate, and lead chromate is what makes that yellow precipitate that's in there. But anyhow, I digress. The whole point of this slide is that the total mass of the substances didn't change, even though there was a reaction. You can clearly see there was a nice reaction, right? There was a reaction here, RXN, I'll abbreviate it. And how do you know that? You can see it with your eyes, right? There was no yellow solid over here, and you can clearly see that there's a yellow solid form. And so we know that there was a reaction, but again, the law of mass conservation was obeyed. So the total amount of matter is going to remain constant even after a reaction. Think about something like combustion, okay? If you sitting around the campfire in the summertime, by a lake or something, and you're burning some wood, and you're sitting there for a few hours and you're burning all these pieces of wood, and you think, well, when I finished burning all this wood, which was a chemical reaction, a chemical change, what I'm left over with is ashes, and therefore, I must have destroyed some of the mass. I don't know where it went. Well, you didn't destroy any of that mass, okay? If you were to collect all of the ash and all of the gases that were produced from that combustion, they would equal the mass of the wood that you started with. It's not intuitive all the time, but the law of mass conservation has to be obeyed. Here's another way of looking at that same law. It's just another slide representing the same thing. Sometimes when you're an instructor in chemistry, it's nice to explain the same thing a couple of different ways. And it says here, again, the total mass of substances does not change during a chemical reaction. So if we take two reactants, whatever they are, and they have an example here, which is calcium oxide and calcium oxide and carbon dioxide. If you combine those two compounds, you can see that we have 56.08 grams of calcium oxide, and we combine that with 44 grams of carbon dioxide, we end up with this new compound. So there's a chemical reaction, okay, there was a change. We formed this compound called calcium carbonate, and the mass is 100.08. Well, looky, if you add up 56.08 and 44.00 on your calculator, you're going to end up with 100.08. And so the law of mass conservation was obeyed. Okay, so the law, and if you're like, what's your point, Mr. Deon? What are you yammering on about? Well, what I'm yammering on about is that you have to be aware of the law of mass conservation. And later on, when we get into the subject known as stoichiometry, and this is something we'll look at in chapter 3, the law of mass conservation is something you can kind of keep in the back of your mind and say, when you're calculating the mass of products, does it make sense, right? Because the law of mass conservation will always be obeyed. All right, with that in mind, let's take a look at a question. And this is just something I put in here for our own personal edification. It says, I can't get away from that wood burning example, can I? It says, when a sample of wood is burned, the mass of the reactants is 100 grams. So notice it doesn't just say the mass of the wood, because you're not just using the wood for the combustion, you're also using oxygen. And so the mass of the reactants is 100 grams. If 15 grams of ash is one product, what is the mass of the other products combined? Who can help me out? I see that Callie already put in the answer, and so did Jordan and Amelia. Yeah, it's 85 grams. And how did we get that? Well, we know that we start with 100 grams. And what they're saying is that the ash weighs 15 grams. So if you subtract 15.0 grams, you end up with 85 grams, okay? In fact, there's a mistake here in significant figures, isn't there? Anyhow, this should say 100.0 grams if the answer is going to be 85.0. Anyhow, let's move on from there. The law of mass conservation, one of those laws you just have to know. Let's move on to another law. If there's one thing I've learned in life, is that science students usually like rules. They're like, just tell me the rules, and then I'll obey those rules and get a good grade, right? Anyhow, so let's take a look at the law of definite or constant composition. And that law is summarized here. It says, no matter the source of a compound, its elements occur in the same proportion by mass. So there's a compound called calcium carbonate. And I know we haven't spent a lot of time looking at the periodic table yet, but I'll just write down here the formula for this compound. It's Ca for calcium, C for carbon, and then O3. So this is calcium carbonate, okay? And calcium carbonate is found in many different places on the planet Earth. It's found in things like marble, and that's This is a marble statue up here on the top, okay? And it's also found in things like coral, like different types of coral. And are there other places you can find calcium carbonate? Of course, of course. But if you were to take some calcium carbonate from this, beautiful marble statue, or take it from a piece of coral, it doesn't matter where the calcium carbonate comes from. It's always going to be the same proportion by mass. It's always going to be 40%, 40 mass percent calcium, 12 mass percent carbon, and 48 mass percent oxygen. Okay, if you're a real math hound, you'll follow me, and I would say, well, if you had 100 grams of it, if you had 100 grams of calcium carbonate, right, how many grams of calcium would you have? You'd have 40 grams, right? You'd have 12 grams of carbon. You'd have 48 grams of oxygen. Okay, so it doesn't matter where we grab a compound, right? If we grab water from a lake in Minnesota, or if we go to, New Zealand and grab it from a lake there, it's still going to be composed of the same elements in the same proportion by mass. And I'm sure that some of you are already thinking like, well, come on, I know that's true, right? Calcium carbonate is calcium carbonate. Okay, but we still need to define these things before we really get moving here. Here's another way of representing the law of definite or constant composition. What did I say? I said for a calcium carbonate, I said if you had 100 grams, right, you'd have 40 grams of calcium, so on and so forth. But what if you had 20 grams, right? What if you had 20 grams of calcium carbonate, CaCO3? Well, if it's 40% calcium, all you'd have to do is multiply 20 by 0.4, right? Because that's the fraction of 1 that it is, okay? So if you had 20 and you multiply that by 0.4, you're going to get 8 grams, right? If you take 20 and you multiply it by 0.12, you're going to get 2.4. And if you take 20 and you multiply it by 0.48, you're going to end up with 9.6, okay? So it doesn't matter how much of the sample we have, okay? It's always going to be have the same mass fractions of the elements that make up that compound. So mass fraction is fixed no matter the size of the sample. That's the take-home message from this slide. All right, with that in mind, let's take a look at a problem. I know my students like to look at chemistry problems. They like to practice problems. You probably noticed that I posted some practice problems with solutions the other day. I posted some practice problems for chapter 1. I also posted the solutions to those. I also posted some practice problems for chapters 2 and chapter 3, but I put a timer on the solution, so they're going to be released way before the exam, but I put them on there so you could give them a try without looking at the solutions manual. Let me just tell you a little something about solutions manuals before I move on. Before looking at solutions, is that a solutions manual can be your best friend, but it can also be your worst enemy at the same time as a chemistry student. And let me explain why that is, okay? So I share my office with another instructor at UCCS. His name is Dr. Diaz, and he taught this class for many, 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 many years. And I always taught organic chemistry, and now I teach both. But anyhow, so the two of us, we teach a lot of students at UCCS combined, and pre-COVID, we had lots of students come into our office with lots of different questions. And oftentimes students would come in and they'd say, Dr. Diaz or Mr. Deon, I did all the practice problems in the book. I did all the practice problems that you suggested, and I still didn't get the grade I wanted on my exam, but I did do all the practice problems, and what we would do oftentimes, most of the time, is we would just open the book and say, okay, well, here's one of those practice problems that you said that you did. Could you solve that practice problem now? And I'd say that 99.9% of the time, the student was unable to do that. Now, if you're like, well, why would that be? The reason why is because if you look at the solution to an answer, okay, every time you solve a problem, okay, you solve problem 1. I'm going to look at the solution. Good, got it. Go to problem 2. Look at the solution. Good, got that one too. Okay, problem 3. Try it. Oh, look at the solution. Oh, I didn't get it. Oh, but I almost had it. Okay, I get it. Move on to question number 4. The problem there is that when you write an exam, you're not going to get feedback after every question. Okay, you're not going to do question number 1 and I'm going to grade it, and then question number 2 and then I'm going to grade it. Right? We grade an exam in its entirety. So I would encourage you to try a plethora of problems before looking at the solutions. Anyhow, with that little speech in mind, let's take a look at a problem. It says here, an analysis of 84.2 grams of the uranium containing compound pitchblende shows it is composed of 71.4 grams of uranium with oxygen as the only other element. So this compound is made completely out of uranium and oxygen. So the atomic symbol for uranium, I'll help you out, is U, and the atomic symbol for oxygen is O. Not much of a stretch on that one, is there? Anyhow, so we have that. It says how many grams of uranium can be obtained from 102 grams of pitchblende? Well, we know from the law of definite composition that we can measure, okay, the percentage, let me just move this down, the percentage of uranium in this compound because we have it in a sample that's given to us right here. Now my marker's getting in the way here, isn't it? But we have 84.2 grams of pitchblende, and we know that it's got 71.4 grams of uranium in it, right? So what's the mass percentage of uranium and pitchblende? Well, we can figure that out. All we have to do is divide 71.4 by 84.2. And then we can take that fraction and multiply it by 102 to get our final answer. Now, if you're not 100% sure what the heck is going on, let's take a look at it over here. Let's solve it. So first, let's solve for the percent mass of uranium in pitchblende. So let's write down here the percent mass of uranium is going to be equal to, I have 71.4 grams of uranium in 84.2 grams of, I'm just going to call it PIT, pitchblende. Okay. Now, if I multiply that by 100%, and I'm just doing that for posterity's sake, I've already gone ahead and done this one for sure, and it's 84.8% uranium. Okay, I can express that as a fraction of 1, right? I can divide that in 100, and I would end up with 0.848 parts by mass, so I'll write that down, or 0.848 parts by mass. Okay. And so now it's asking me how many grams of uranium can be attained from 102 kilograms of pitchblende, right? I've already figured out what the mass percentage of uranium is in pitchblende. All I have to do is multiply that by the mass of my sample of pitchblende, which is 102 kilograms. And so let's write that down. So we'll put, therefore, 102 kilograms of pitchblende multiplied by 0.848 parts of uranium. Okay. Go. Divided by pitchblende, right? Because we have 0.848 parts uranium in any sample of pitchblende taken from anywhere in the universe. Okay. So all I have to do now is my pitchblende is going to cancel out, and I end up with 86.5 kilograms, like that. So I have 86.5 kilograms of uranium in that sample. Now I see some, yammering on here, or I see some discussion here about grams and kilograms. Remember, I didn't have to, like Brittany says, he'll convert it. Grams doesn't matter for solving this part of the problem, the second part of the problem, right? The first parts, right, the first things they give us are 84.2 grams of pitchblende containing 71.4 grams of uranium. All I used that for was to solve the mass percent of uranium in pitchblende. Okay, now I could multiply that by anything. It could be a 102 kilogram sample. It could be a, 75 quintillion, femtogram sample. It doesn't matter. That's not important. Okay, what's important here is that we were able to determine the mass percent of uranium and then multiply that by the size of our sample. And now we know how much uranium is in that 102 kilograms of pitchblende. All right, let's move on from there. And here's the solution, and I like to include those. Let's see here. Let's try one more. I might skip some of these today. I put in a lot of questions here. Anyhow, it says, what does it say? It says, suppose that 2.83 grams of a compound that is made of only lead and sulfur, right? All capital letters. I'll help you out here. So lead, the atomic symbol for lead, I told you is Pb. And it's a lot easier to remember because in French, lead is plomb, which is Plomb. Anyhow, and you've probably heard of a plumber before, and pipes used to be made out of lead. Ah, there's a connection there. Anyhow, in sulfur, the atomic symbol for sulfur is S. Anyhow, you have some kind of compound. You don't know what the hell the compound is, but it says you got 2.83 grams of it, and it was analyzed in a lab somewhere, and it was found that the sample had 2.54 grams of lead and 0.380 grams of sulfur. Calculate the mass percentage of lead and sulfur in the compound called lead 2 sulfide. We'll look at that. They even tell us what the compound is. Anyhow, we don't even need that information to solve the problem, right? All I need to do is divide the masses of lead and sulfur by the total mass. So let's figure out what the percentage of lead is first, because all of the answers have lead listed first. So let's do that. So let's see here. The percent lead is going to be equal to, what is it, 2.45 grams divided by 2.83 grams. Those units cancel. I'll multiply that by 100%. I've done that over here on a piece of paper. Anyhow, and I get 86.6% lead. So this must be the answer. And if you take 100 and you subtract 86.6%, you're going to end up with the rest, which is sulfur, which is only 13.4%. There you have it. Give me a thumbs up if you think you can solve that one. All right, I'll take it. Great, good. So let's move on and talk about what's called the law of multiple proportions. I'll kind of go over this law rather quickly because we see it manifested just about every day in chemistry class. You just see it all the time. But the law of multiple proportion states that if elements A and B, so if you have two different elements and they can react to form two or maybe more different compounds, the different masses of B that will combine with a fixed mass of A can always be expressed as a ratio of small whole numbers. Now, it says here, take a look at the example, which is carbon oxides A and B. So there's two kinds of carbon oxides. You've probably heard of both of them, right? I'm sure you've all heard of carbon dioxide, right? And carbon monoxide, sometimes they call it the silent killer. Anyhow, so these are the two oxides of carbon. And if we analyze them according to their mass, just like we just did, that carbon monoxide, or carbon oxide 1, that they're calling it here, is 57.1% oxygen, 42.9% carbon. If we look at the second carbon oxide, it's 72.7% oxygen, and the remainder of the percentage is carbon. So again, what the law of multiple proportions is saying, though, is that the masses should be able, or we should be able to express those masses as small whole numbers. So numbers like 1, 2, 3, 4, so on and so forth. All right, so let's see, can we do that? We can totally do that, and that is demonstrated here on this slide. Now it says assume, it's an easy assumption to make, that you have 100 grams of each compound. It says here, if you imagine that you have 57 grams of carbon oxide 1, or sorry, 57 grams of oxygen in carbon oxide 1 and 42.9 grams of carbon in carbon oxide 1, blah, blah, blah. Anyhow, if you make a ratio of those, you see that you get 1.33, okay? You can do the same thing with carbon oxide 2, and you get a ratio of 2.66. Well, can we express those as a ratio? And the answer is yes. If we divide those two, we see that we have a ratio of 2 to 1. And so we're able to do that. We obtain a ratio of small whole numbers. And if you're like, oh, wow, Mr. Deon, I'm kind of confused. Look, it's going to be, I think if you stick with it, it will become more clear. But I would say one of the major take-home messages from this slide is something that's not mentioned in the book. And I'll just throw it out there, and don't write this down. In fact, I might edit the video after because I feel dirty doing this. But there's no such thing as like CO 2.28 or something like that, okay? You're never going to have atoms combining where you have this one, you have one of these, and then 2.28 of those. Never going to happen. They're always going to combine in simple whole number ratios. In fact, let me erase that so that there's no record of it. All right. Well, let's move on from there. And I'm going to backtrack to the very beginning of this chapter. If you are an avid reader of Silberberg's textbook, she goes all the way back to the beginning of history and kind of talks about where the word atom comes from. Okay, where the word atom comes from. And if you think about taking something like, and the example she uses is the one, I'll just steal it from her. She said, imagine you were to take a sheet of aluminum foil, right? Everybody has probably some aluminum foil in their kitchen. And imagine you took that piece of aluminum foil and you cut it in half. Right now, imagine you took the left side and you cut that in half, and then you took this piece and you cut it in half, 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 and cut it in half, and cut it in half. Hold on, let me blow that up. I'm kidding, but anyhow, I'm sure that somebody in the class has had this thought, you know, at some point in their life, like, what if I cut a piece of matter and just kept cutting it down? Like, when I get down to something that's indivisible? Well, the Greek philosopher Democritus proposed that you could cut matter down into something that he called an indivisible particle, and there's probably more information in the book about that. And he called that particle atomos. And atomos, that idea stuck around for a long time, but it took about 2,000 years, a little more than 2,000 years, as a matter of fact, until an English school teacher named John Dalton came along in 1803, and he postulated what's called, or published, Dalton's atomic theory. And Dalton's atomic theory was just a breakthrough in science. And what his hypotheses are, or were, and mostly hold true today, is that all matter consists of atoms. Okay, so everything consists of atoms, whether it's a student or a textbook or a statue, whatever. Everything consists of atoms, tiny indivisible particles of an element that cannot be created or destroyed. Atoms of one element cannot be converted into atoms of an element of another element. And I'm sure that there's somebody, oh, probably not, I'm just being silly, but there might be somebody at home who's thinking, oh, fiddlesticks, you know, now I can't convert that aluminum into gold, darn it. Okay, atoms of an element are identical in mass and other properties and are different from the atoms of any other element. Now, I'm sure there's somebody in the class who's taken maybe high school chemistry or maybe even AP chemistry in high school, and you've probably heard of the concept of isotopes, and you're like, well, that doesn't hold exactly true. And you're right, okay, but we're going to address that later on. Okay, let's take a look at the fourth one. Hey, look at this. Compounds result from the chemical combination of a specific ratio of atoms of different elements. So that's something that we looked at already. All right, well, what's neat about Dalton's atomic theory, and I don't want to spend a lot of time on this. You can maybe spend some more time reading this in the textbook. I'm not going to ask you a million questions about how Dalton's atomic theory was used to explain the law of mass conservation. So we said that matter can't be created or destroyed, so the mass of the reactants is going to be equal to the mass of the products, and you see how that is in line with Dalton's atomic theory. You see that postulate 1 says that atoms can't be created or destroyed. You can't convert them into other types of atoms, and every atom has a fixed mass. So since they all have fixed masses, that during a chemical reaction, the same atoms are present. They're just going to be there in what? Different combinations. They're just going to rearrange, and therefore there's no mass change overall. So if you're wondering, you know, what's the point behind this slide, Mr. Deon? The point is just using Dalton's atomic theory to explain the law of mass conservation. I think there's another example in here. This is just showing Dalton's atomic theory and how it explains the law of definite composition, which we already looked at. So I'm not going to spend a lot of time on this. Postulate 4 says atoms are combined in what? Specific ratios. Each atom has a specific mass, and so each element constitutes a fixed fraction of the total mass in a compound. So nothing more than just proving these laws using Dalton's atomic theory. The law of multiple proportions is also proved. I'm going to let you read that, and we're going to move on to a problem. Okay, so it says here, visualizing the mass. So this problem here, let's see, what does it say? Sorry, I'm rifling through my notes here at the same time. What time is it? 10:05? This class goes till 11:05, right? Good. Okay, so it says here, I'm kidding. It says here, the following scene represents an atomic scale view of a chemical reaction. Oh, what a beautiful reaction. Which of the mass laws, mass conservation, definite composition, or multiple proportions are illustrated? This is kind of interesting problem here. All right, is everybody with me on this problem? Are my students out there? I know there's probably 100. Good, Blake is here. Good enough. I'll take it. Thanks, Blake. Okay. The reason why is you can imagine, and I know that you probably feel the same way as me, but
Hey, Mr. Deon.
Yeah.
Message in there. For some reason, every time the class responds, it blocks my ability to put input. So
Okay.
I'm just bringing that to your attention. You didn't respond via chat, so I just don't want you to think I'm not participating.
Oh, I know you're there, and I appreciate it. I really appreciate that feedback.
Okay.
I appreciate it very,
Thanks,
very much. Yep. Thank you.
Okay.
It's always good to know that somebody's out there because I'm literally staring at the wall while I'm teaching. And anyhow, so let's see here. It says the following scene represents an atomic scale view of a chemical reaction. Which of the mass laws, mass conservation, definite composition, or multiple proportions is illustrated? Now, it says here, it's a really good plan, okay? It might not be intuitive, but what she's saying here, what the author of our book is saying here, is she's saying make a special note of the numbers and the types and the combination of atoms before and after the reaction. Like, for example, if we look at the reactants, you can see that we have 1, 2, 3, 4, 5, 6, 7. We have 7 purple. We have 7 purple atoms. I don't know what atom that is. And we have 4, 5, 6, 7, 8. We have 9 green atoms, right? And let's look at the products. We have 1, 2, 3, 4, 5, 6, 7. So we still have 7 purple. 1, 2, 3. Yeah, we still have 7 purple and 9 green. So we have the same there. And so we've definitely demonstrated the law of mass conservation. Heck yeah. The law of definite composition is also shown, right? Because you can see here that when we form these compounds, we have a 2-to-1 ratio of green to purple in this new compound that's formed. Okay, so we've shown the law of definite composition. The only thing that's not illustrated here is the law of multiple proportions. And if you're like, why is that not shown? Because remember the law of multiple proportions, remember we said we had something like carbon monoxide and carbon dioxide. Well, here we only have that one compound, right? We only have the one with a compound with the one purple. Sorry, I'm making a mess here with the one purple and the 2 greens. Okay, so they're all the same. And so the law of multiple proportions is not being demonstrated here. Anyhow, it's kind of a weird problem, but it works. And here's the solution, and you can spend some time looking at that if you want. All right, strap your skates on, Gordy. We're going in. Okay, we're going to do something completely different now, and we're going to talk a little bit. And this is one of those situations where Mr. Deon really has to be careful to not ramble on too long, because sometimes I can really get into talking about the history of the atom, but I actually went and looked at the textbook this morning, and it's covered in like a few paragraphs. So I'm going to try to summarize this very quickly. Also, I'll point this out, is that there's a great video. If you go in the e-text, there's a very good video. Good video. Okay, I mean, they're really well done. There's actually 3 of them, I think, or 3 or 4 of them, to help students understand the history of the atom. Just very well done, summarizes it very well. Anyhow, scientists knew that matter and charge were related because of things like static electricity. And they also knew that electric charge, like from lightning, let's say, could decompose some compounds into elements, but they had no idea what the current was made of, right? They had no idea. And so what a scientist named J.J. Thomson did is he did an experiment with something called a cathode ray tube. And a cathode ray tube is kind of like a precursor to the old-timey television set, in case you've never seen an old-timey television set. Anyhow, I have. I grew up with one. But anyhow, I digress. So we have a cathode ray tube. It's basically just a big glass tube. Let me get a different color here. Where's my pen? Here it is. There we go. Put you away. So it's basically a big glass tube with most of the air evacuated. And then it has 2 metal electrodes placed in one end of it. And then they hook those electrodes up to a really high voltage source. And when that was done, what they noticed is that there was like a beam of particles that went from the cathode, which is negatively charged, to the anode, and then through the anode, which had a hole in it. Might be hard to see in my slide. And then that beam, which is called a cathode ray, ended up causing some kind of phosphorescence, or fluorescence, I should say. I guess it would technically be phosphorescence on a phosphor-coated end of the tube. Okay, and they didn't know what that ray was made out of. Now, I'm sure you're like, well, it's made out of electrons. But anyhow, they didn't know that at the time. And so what Thomson did is he did some experiments with that cathode ray. And he took it and he exposed it to a magnetic field just with a magnet. Now, before I mention, what happened is that a tiny charged body that is moving will behave like a little magnet. And so since the ray bent in the magnetic field, okay, so he saw the ray bent either up or down, anyhow, so it bent, he could conclude that that ray was made out of some kind of particle that was charged, okay? So that's number one. Now, number two is he decided, okay, well, what would happen if I exposed it to an electric field, okay? So he has a positive and a negative terminal, and what he noticed is that the beam was deflected away from the negative end of the electrode. Well, hey, we know that opposites attract and like charges repel. And so not only could he conclude that he had charged particles, but that they were negatively charged, okay? Also, he decided to swap out the metals here, the metals that were used, and he found that he always had the same cathode ray, and so he determined that these particles were present in all matter, okay? And there's some more history here, and the book doesn't tell you the entire story, and there's obviously some physics here that's beyond the scope of our course, but I'll just kind of tell you something here, is that he was also able to determine that the particle had about 1,000th the mass of a hydrogen atom, okay? And if you're like, well, what's the significance? The significance is this, is that scientists knew of atoms, but they didn't know that there was any particle smaller than an atom. And so since he discovered a particle that had a mass much less than a hydrogen atom, okay, which is the lightest atom known, they said, okay, well, atoms must be made of particles that are even smaller. Now, what else can we get from this slide? There's a lot of information on one slide, huh? Well, matter is neutral, right? If I have a stapler in front of me on my desk, if I go grab my stapler, I didn't get a shock, okay? I'm holding my Apple Pencil, I'm not getting a shock because matter is neutral, right? So matter is neutral, so that means there has to be some kind of positive charge to balance that out. And we're going to talk about that in a second. But before we talk about what a proton is, I want to talk more about electrons. Okay, I'm not going to show you the movie, but Emma posted in the chat, she said, I recommend watching it. I do too. I strongly recommend watching this video. Anyhow, let's move on and talk about Millikan's oil drop experiment. And again, I'm going to try to not go into too much detail here. But basically, what Millikan did is he was able to determine the mass of an electron. And you're like, well, how the heck did he do that? Because Thomson, and I should back up here, but I won't, Thomson determined the mass to charge ratio of an electron. I forgot to say that, but he did determine that, okay? So he knew the amount of mass per charge, okay? And what Millikan did is he took this apparatus that's shown here, and he took oil in an atomizer. So this is what's called an atomizer, and you might be thinking, come on, Mr. Deon, it looks like a perfume sprayer to me. It's basically what it is, okay? It's nothing more than a perfume sprayer, and it would spray these little tiny oil droplets, and then he had these two charged plates here, okay? And he had a hole in the positively charged plate. And some of the drops, which might be hard to see, but some of the drops would fall through that hole, okay? So now we've got oil droplets falling through a hole. You're like, boy, this is entertaining, Mr. Deon. Well, let me tell you even more. You're gonna fall over in your seat, okay? So what he did then is he took an X-ray source and he bombarded the air inside that chamber with X-rays, which caused electrons to be basically removed from the molecules in the air, and those electrons coated the oil droplet. So now we've got an oil droplet, okay, and it's coated in electrons. Okay, this is me really grasping at straws here, but it's basically coated in electrons. Now the electron is obviously a lot smaller than that, and I'm not going to fill them all in. So now you've got an oil droplet coated in electrons. You're like, wowie wow. Okay, so then what he did, he was able to change the charge, or what's the word I should use here? Mitigate the charge of the positive electron. And since electrons are negatively charged, he had a dial, okay? And he could crank up that dial, he could crank that up so that the oil droplet coated in electrons would be attracted to the positively charged plate, okay? And then using some, well, it's actually not that sophisticated, but I'm going to skip over it. Using some math, he was able to determine what the overall charge of the oil droplet was. Okay, so he was able to determine the overall charge. And then he determined that even though the oil droplets varied in size, that the charge on the oil droplets was always some multiple of this number here, negative 1.602 times 10 to the minus 19 coulomb. So he multiplied that by Thomson's mass to charge ratio, and he was able to determine the mass of an electron, which is 9.09 times 10 to the 28 grams. Now, I probably spent a little too much time on that, but it's pretty fascinating stuff. Not my favorite experiment in the history of chemistry, but it's pretty darn good, okay? So you should know that Millikan was the one who determined the charge of an electron, the mass of an electron. Anyhow, and then in terms of how did they discover the proton? Well, scientists knew, well, there's got to be some kind of other particle that balances out the negative charge of an electron. And another thing I'll just point out here is that electrons, their masses are so small that it didn't account for the mass of atoms. So the mass of an atom is so much bigger than the mass of an electron that they were like, well, whatever's positively charged must weigh much more than an electron. This doesn't make any sense. And so Ernest Rutherford was a scientist from New Zealand, and he did this really interesting experiment. And I'll go over this kind of quickly. Basically, what he did is he took what are called alpha particles, and he used some kind of radioactive element, and he bombarded gold foil with these little tiny particles, these little radioactive particles called alpha particles. And what happened is that scientists at that time proposed that an atom was made up of electrons, and they were just kind of distributed throughout this kind of positive matter, okay? They actually called it the plum pudding model. So over here in the States, we don't eat plum pudding a whole hell of a lot, but what they thought is that they had all this negative charge distributed throughout something that was basically a big, positively charged. So all that I'm shading in here in red, they said, okay, well, all of this is positive. It's just floating around. Maybe in the States, we could call that the chocolate chip muffin model or something. But anyhow, so what Rutherford did is he said, according to this model, the blueberry muffin model or the plum pudding model, he said, I'm going to take these little tiny particles and I'm going to fire them at a sheet of gold foil. Now, here's the sheet of gold foil down here, okay? And if you were to take your eyeball and look on the side of that gold foil, here is the edge of the gold foil, okay? And he said, well, the atom just has some electrons kind of distributed throughout this positive, blob of matter, okay? And so the the alpha particles are just going to go right through the gold foil. But what he saw, or what they noticed, was something really amazing, is that most of the alpha particles did go through the foil, but some of them bounced back. And you can see that manifested right here, okay? And it was actually his graduate student, I believe, Geiger, that came back and said, you're not going to believe this, but about 1 in 20,000 of these little alpha particles are bouncing back at us. And the famous quote from the paper or whatever from Rutherford is that he said, it's like you took a 15-inch cannonball and fired it at a piece of tissue paper and it bounced back at you. So they had no idea this was going to happen. But basically what that proved is that in the middle of the atom, there is a very tiny, positively charged piece of matter in there, and it's called the nucleus. And the positive charge in there, they called it the proton. Now, obviously, this is just kind of an abridged version of the history of the atom. If you're really into the history of the atom, and I'm not going to, this isn't a chemistry history class, but if you're really fascinated by that, you could, of course, spend all manner of time looking at that. But let's just move on from there and say that an atom is an electrically neutral spherical entity composed of a positively charged central nucleus in the middle, surrounded by one or more negatively charged electrons. The atomic nucleus consists of protons and neutrons. So electrons are negatively charged. So electrons are negative, protons are positive, and neutrons are neutral. They have no charge. Okay. Now, again, you can look at the textbook to get more information about the scope or the scale of how small a nucleus is compared to an atom. But I'll just put it like this: if you had, let's say you took the Coors Field or something, and you took a pea and put it in the middle, right? That pea would be the size of a nucleus compared to the size of the entire atom, right? The pea versus the entire football stadium or whatever. Okay, so a nucleus is very small and very dense. So here are properties of 3 key subatomic particles. This is a great summary. So we have a proton. It has a charge of +1. We have a neutron, which is neutral, and we have an electron, which has a charge of -1. These little symbols here are the symbols that I will use sometimes for a proton, neutron, and electron. Sometimes I even leave the superscripts out. Okay. We have the absolute charges in Coulomb. We have the relative AMU. So AMU stands for atomic mass unit, and I'll discuss that more with you later on. But anyhow, I want you to note that the mass of a proton and a neutron, they're pretty similar, okay? They're both pretty close to each other. It's not until you get into these digits here that they're different. They're both around 1.67 times 10 to the minus 24 grams. And they are both about roughly 1,840 times heavier than an electron, okay? Again, the proton and the neutron, they reside in the nucleus, which is in the center of the atom, and the electron is outside of the atom. All right, so that's quite a bit about the structure of an atom and a little bit about the history of the atom. And from there, let's move on and talk about atomic symbol, number, and mass. So let's really get down to brass tacks here. I would recommend always having a periodic table by your side in this class from now on, from today and until the class is done, okay? I would recommend familiarizing yourself with all of the names of the elements. As a matter of fact, you're like, well, which ones? All of them. I would take some time and I would look over all of the elements. If you have a hard copy of the book, which I know most of you don't, it has a whole list of all the elements in alphabetical order by their name, and their atomic symbols are in there, so you might be wise to do that. Anyhow, when you look at the periodic table, you'll see in each one of these little squares or blocks that's in the periodic table, you'll see an atomic symbol, and that's the symbol of the element. Oftentimes, you'll see a number as a superscript and another one as a subscript. The number at the top, we call that the mass number, and the number at the bottom here, we call that the atomic number. Now, the mass number is the sum of the protons and the neutrons. So if I have, let's say, 10 protons and 10 neutrons in an atom, I would have a mass number of 20, right? 10 plus 10 is 20. The atomic number, however, okay, the atomic number is what I consider, it's the identity, okay? It's the identity, so, of the atom. All right, the atomic number is the number of protons in a nucleus, okay? It's not very often that Mr. Deon really slows down his speech, but I'm going to slow it down here for a second for you. The number of protons is what gives an atom its identity. It's not the number of neutrons, and it's not the number of electrons. If you look at the periodic table and you look at element number 1, okay, it's hydrogen. Hydrogen has 1 proton, and that's why it's element number 1. If you look at element number 2, it's helium. 2 means that it has 2 protons. If you skip all the way down to element number 35, it's bromine, and that means that bromine has 35 protons. Okay, so the atomic number is the number of protons, and that is what gives an atom its identity, not the number of neutrons and not the number of electrons. Let's take a look at some examples shown here on the bottom right. We have carbon, we have a mass number of 12, and we have an atomic number of 6. Well, if we have an atomic number of 6, that means that we have 6 protons. Well, what plus 6 gives me 12? The answer is 6, and therefore I must have 6 neutrons. The same rationale applies to oxygen. So we have this oxygen, we call it oxygen 16. Okay, so Oxygen 16 has an atomic number of 8. What does that mean? It means it has 8 protons. Okay? Oxygen 16, what plus 8 gives me 16? Well, the answer is 8, so I must have 8 neutrons. Now let me add a little bit more to this. Both of these atoms, neither of them have any charge indicated with them. Well, how would I balance out 6 protons? I must have 6 electrons. How would I balance out 8 protons? I must have 8 electrons. Okay? All right, so that's a little bit about atomic symbol, number, and mass. And let's move on and talk about the subject of isotopes. If you ever watched The Simpsons, you probably heard of the Springfield isotope. It says here, isotopes are atoms of an element with the same number of protons, but a different number of neutrons. Isotopes have what? The same atomic number. Why would that be? Because they're the same element, okay? But they have a different mass number. Remember, I told you that an element is always identified by the number of protons. So let's take a look at these two beautiful isotopes right here. We have uranium-235 and uranium-238. Notice that on the last slide that oftentimes when we're describing an element as an isotope, we say the name of the element and then we read off the mass number. So we have carbon 12, oxygen 16. Down here we have uranium-235. Why? Because 235 is the mass number. Here we have uranium-238. Why is it 238? Because 238 is the mass number. All right, so now that we've got that clear, what makes these two isotopes different? Hey, look, they both have the same number of protons. They both have 92 protons. Okay? They both have the same number of electrons because there's no charge indicated. What makes them different is the number of neutrons. Now remember, mass number is equal to the sum of the protons and the neutrons. And therefore, the way that they determined, or the way that the author determined that there was 143 neutrons was they said, well, if I have a mass number of 235 and I subtract 143, I end up with 92. Okay? The same thing applies here. And I actually should have written it as 235 minus 92. That might have made more sense. In fact, I'll even back up. If I take 235, subtract 92, I get 143. If I take 238, Mr. Deon's getting tired. I take a different isotope, so 238, and I subtract 92, I end up with 146 neutrons, okay? So again, do these two isotopes have different masses? Absolutely they do. Absolutely, but are they different elements? No, they are the same element. They just have different masses. And why is that? Because they have a different number of what? They have a different number of neutrons. All right, so that's what an isotope is. Okay, with that in mind, let's take a look at a problem. It's 10:28 and class goes till noon, so let's get started here. Let's see. Yeah, okay, sorry, just finding my notes here. It says silicon, which is abbreviated Si, has 3 naturally occurring isotopes, silicon-28, silicon-29, and silicon-30. Determine the number of protons, neutrons, and electrons in each silicon isotope. I hope, did I put the answer there? Oh, fiddlesticks. I don't like having the answers. Okay. All right, so let's take a looky here. So let's start with silicon-28. Why don't we just do that one, and then you can figure out the rest. But if I have silicon-28, so let's write that down here. Could anybody tell me what the atomic number of silicon is?
14.
Yeah, absolutely. It's 14. So silicon is element number 14 in the periodic table. All right. Silicon-28, and silicon always has 14 protons. And so for silicon-28, we'll say the number of protons is 14. There's no charge indicated, so the number of electrons is 14. And the number of neutrons, well, let me do some mental math here. If I take 28 and I subtract 14, that would mean that I have 14 neutrons. All right, so there we go. All righty, so let's take a look at the solutions for the rest. So I'll put them over here. So you do the exact same exercise to figure out the number of neutrons for silicon 29 and silicon 30. Give me a thumbs up if you think you could solve for the number of protons, neutrons, and electrons. All right, good. Great. As they say in Scottish, great. All right, well, let's move on from there and talk about atomic mass. Sorry. There's a lot of us online right now, so my chat's a little slow at times. Anyhow, my MacBook always sounds like it's ready to keel over. Anyhow, let's take a look at atomic mass. Boy, that's talk about your fuzzy slides. Can't even read these masses, or I can barely read them. But anyhow, you can see the ones that are highlighted here for potassium, gold, silicon, and antimony. Anyhow, you'll see here that when you look at the periodic table, you might have noticed something. You're like, something's a little fishy here, Mr. Deon. I thought you said mass number was the sum of protons plus the number of neutrons. But then if I look at potassium, right, I see an atomic mass of 39.10. If I look at gold, it has a mass of 196.97. Silicon has a decimal, and so does antimony. Where the hell did these decimals come from? All you've been talking about is whole numbers. Whoa, 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 hold the phone, okay? The atomic mass that you see on a periodic table is a weighted, oops, I meant to use a highlighter there, is a weighted average, okay, of the isotopic masses, okay? So what we've done, or what scientists have done, is they've taken the weighted average of the isotopic masses and put those as the atomic masses in the periodic table. And that takes into account the abundance, or the relative abundance, of different isotopes. So a little bit of history here. It says Dalton was able to determine the relative masses of atoms, and he based his whole scale off of what he called the atomic mass unit, and he used hydrogen for it. Now that's just historical. You don't need to worry about the history there. But now we don't base it on hydrogen 1. We base it off of carbon 12. So IUPAC, which is the International Union of Pure and Applied Chemistry, uses carbon 12 as a standard, and they say that carbon 12 is 12 atomic mass units exactly. And unbeknownst to me until just like a while ago, the AMU is now replaced with the U. Anyhow, whatever. It says it right here, AMU is replaced by the U. You know what? Mr. Deon still likes the AMU. I used it for most of my life, so I'm still kind of dig it. But anyhow, the atomic mass unit now, so if you have one atomic mass unit, it's based on 1/12 of carbon 12. So, and it mentions that in the textbook, but basically you take carbon 12 and you divide it by 12, and then you get 1 AMU. So that's the 1 AMU, or the 1U, if you want to get down with it nowadays. Anyhow, but that's where the atomic mass unit comes from. Anyhow, it says that each element in the periodic table is displayed with a unique atomic mass. Also, before we move on, I'll point out something here that I'll bring up more in chapter 3, which it says U, or the atomic mass unit, is equal to the number of grams per mole. I'm sure that some of you are perfectly aware of what a mole is. It's something that lives in the ground, but in chapter 3, I will go on and talk in much more detail about the mole. All right, well, with that in mind, let's take a look at a problem. I can tell you right now that I've taught chemistry and I've studied chemistry long enough to know that every first year final exam in chemistry always has this question, something basically just like it. Okay, it says you have some silver. Silver has an atomic number of 47. You can see it sandwiched right in between palladium and cadmium in the periodic table. Silver has 2 naturally occurring isotopes, silver 107 and silver 109. From the mass spectrometric data provided, calculate the atomic mass of silver. Okay, so they've given us the atomic masses of each isotope of silver. Okay, so if you measure the isotope silver 107, okay, so silver 107, if you measure that isotope in atomic mass units, what's the atomic mass unit? 1/12 of carbon 12, it actually weighs 106.90 something spinach, okay? Now, it's about, or it has a relative abundance of 51.84%. So we only have that. So if we have a mixture of silver, right, 51.84% of it is going to have the mass of 106.90, blah, blah, blah. 48.6% of it, 48.16 rather, percent of it is going to have this mass, 108.904.76. So how the heck would we do that? All we have to do is find a weighted average. Nothing more than that. And if you're like, Mr. Deon, is that all I have to do is just find a weighted average? Heck yeah, nothing else. Let me show you how you do that if you're unsure how to find a weighted average. Okay, all I'm going to do is I'm going to take 106. So let's put here atomic mass. I'll be a real teacher here. Atomic mass of silver is equal to 106.90509 multiplied by its relative abundance. We'll express it as a fraction of 1, which is 0.5184 plus 108.90476, and we'll multiply it by 0.4816. Again, I'm just expressing the percentage, and I'm just dividing it by 100. 0.4816. Now, I solved this, but I didn't go through all the details, did I? Oh, fiddle paddle. Anyhow, look, I have it in the solution over here. So when you punch all of that into your calculator, what you end up with is 107.87. Okay, so you end up with 107.87, and that is the correct number of significant figures. So AMU is our units. And you should make sure that you can do that math, right? You solve the brackets first, okay? Anyhow, so you end up with 55.42, 4 sig figs, plus 52.45, 4 sig figs, and you add those together. You're going to have 2 decimal places, and you end up with 107.87. Let's go to the periodic table. I'm lifting my eyes here, and I'm looking at my periodic table of elements, which is taped to my wall, and it says 107.87. Hot dog, we have a wiener. Okay, it works. All right. Well, in the interest of time, we have 3 minutes left. I'm going to skip the next question. I've got a lot of questions in here. And what I expect you to do before class on Monday is I expect you to read the rest of this chapter. And I also want to point out that, let me just show you, we've got all kinds of interesting things to talk about here, metals and metalloids and blah, 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 molecules and ions and carbonates and chemical formulas. Okay, so you can see here, this is slide what? I don't know, slide 52. Okay, get this out of the way. You can see the right here, chemical formulas. Are you guys ready for some good news? Okay, so I have videos on my YouTube channel, videos that cover chemical formulas and almost all the remainder of this chapter. So chemical formulas and the rest of the chapter, virtually all of it, I have covered in a beautiful 6-part series. They're like, wow, Mr. Deon, thank you for things to watch on my spare time. But why I'm telling you that is because I've taught this class enough to know that chemical formulas is one of those areas of chemistry that I could sit here and lecture it to you for days and days and hours and hours. But what it really takes is some good practice, okay? And so you have to spend a lot of time practicing what is called nomenclature, which is the naming of compounds. And so what I would recommend that you do before class on Monday is spend the time watching those videos. They're not that long. And spend some time memorizing what are called the polyatomic ions. So polyatomic ions are found in table 2.5. It says common polyatomic ions. I would try to memorize all of those before Monday's class. And you're like, oh, Mr. Deon, that's a lot. Like I said, learning chemistry is like learning a language, and there's always a lot to memorize at the beginning. But what will you gain from that? Is it will help you understand what I'm saying. It will help you understand the book. And it is imperative that you know how to name compounds in order to progress in the class. Remember, chemistry is an additive subject. What you use in chapter 1, You're going to apply it in chapter 2, chapters 1 and 2. You're going to use those in chapter 3. You're going to use everything in chapter 4, right? So it kind of builds up like that. And that's why you have to know how to name compounds. All right, anyhow, it's 10:40. I've already taken up too much of your time. Make sure to look for my announcements. I will post probably an announcement with the playlist that has those videos that I just spoke of. And of course, I will post the link to this video, or I'll post this video on my YouTube channel under the playlist that is Chemistry 1401 Fall 2020. And I'll also post the link on Canvas. All right, it's 10:41. I'm breaking the rules. So have a good weekend. Make sure you get that Learn Smart done ASAP. It was good to see you. Thanks for coming to class. I really appreciate my students who show up to lecture on Microsoft Teams. I know it's not easy. I really know it's not. It's not a lot. I don't relish teaching from my basement nearly as much as I enjoy teaching my students. I don't know any of your faces, and it kind of breaks my heart a little bit. I really enjoy getting to know my students, but maybe that's something we could look forward to. If you want to take General Chemistry 2, I'm going to be teaching it in January. So maybe we could get back to face-to-face then, and I would love to meet all of you face-to-face at that time if we can do that. All right, well, I wish you all a very good weekend, and heed my advice, and take care.
Thank you.
You're welcome.